Thanks on everyone. Let's start off. Great. Last thing we have started with angular velocity, omega, and all that stuff. Great. Let's go ahead. Let's do a few more questions before going ahead. A particle is projected with even theta. Gravity is g. This is the origin. Find angular velocity of the particle as seen by the origin when it is at h max. Yeah, let's get this thing. Others do keep your cams on. Karthik, Manav, Manish. Let's give it a try. So when the particle is at h max, like I said, what is omega? See, omega is not defined only for a circle. You can actually define for any theta. If a particle is going in some random curve, then the angle subtended with the reference is your angular position. If you differentiate that angle, you will get omega. Yeah. Let's get the main equations there. It's a little lengthy answer. Let's see. So as the particle is at h max, what is the velocity of this? This will be u cos theta. Now from here, if you draw a line, this is your r bar vector. And let this angle be alpha. So now if you resolve the components, right? So we will get here, this will be u cos theta, cos alpha, and this component will be your u cos theta sine alpha. And if you remember last time we discussed, this is your v tangential. This is the component which is responsible for your angular velocity. And let this distance be small r, which can be found from here. This will be your h max, and this will be your range r by 2. So from here we get tan alpha is h max 2h by r. And then small r is nothing but root over h square plus r square by 4. Yeah, numbers are given, it would have been great. So from here we'll get angular velocity omega, which is v tangential by r, which is u, which is given cos theta. I know sine alpha I can figure out from here by small r is this guy, root over h square plus r square by 4. Clear with this? There, that's how you get it. So, and if you remember what is u cos theta cos alpha? U cos theta cos alpha, this is responsible for changing the distance. So this is d mod r by dt. If you guys remember this, you have done this in kinematics. That component is responsible for increasing the magnitude, whereas this component, the u cos theta sine alpha, is responsible for changing the direction. So this is your radial velocity. We have done this in kinematics, a similar one. Clear? Next one. We have a wall here. You have a laser light. This is a laser spot. You are rotating this laser with omega, which is 0.1 radian per second. So you have taken a laser and you're moving it on a wall. The distance from here to here is 500 meters. And let this angle be theta. Now, if you're moving this thing up, right, so this laser light will actually move on the wall. The laser spot moves on the wall. So next moment, what will happen? The laser will fall here. Next moment, it will fall here. It will be here. It will be here. So it's going up. Find the velocity and acceleration when theta is 60 degrees. Find velocity and acceleration when theta is 60 degrees. So I hope the question was clear. There is a wall at a distance of 500 meters. You took a laser and you're shining it onto the wall and you're moving it up. So the P will continuously keep going up. What will be the velocity and the acceleration when theta is 60 degrees? Let's give it a try. This is more of a kinematics thing, but yeah, the theta is changing there. 250. We have two different numbers. Get me the acceleration also. Hmm, 200 looks right. Right, Ahana. You got it. Right, Yukti. Get the acceleration also. 40 root 3. Okay, I'll give another 45 seconds, 1 minute. Let's see. Then I'll give the acceleration. Everyone should try. Let's see. So let this be y. And this is just brute force differentiation. So from here we get tan theta is equal to y by 500. So y is equal to 500 tan theta. You want velocity? Differentiate it. So velocity of point P is dy by dt. It's only going up. That is 500 tan ka differential is x square theta d theta by dt. And d theta by dt is nothing but omega. That's 500 omega secant square theta. You know omega ka value, you know theta ka value, substitute. You want acceleration, differentiate this again. dvp by dt. 500 omega is constant, then you need to differentiate sec square theta. So this is sec theta ka whole square, chain rule everyone. That's 500 omega, 2 times sec theta. And sec theta ka differential is again sec theta tan theta. Then again you have to differentiate d theta by dt. So you have to keep doing it till you get d theta by dt. That's 1000 omega sec square theta tan theta, and d theta by dt is another omega, so omega square. Substitute, check it out. That should give you the answers. I think this would be 0.01, that will be 10, that will be root 3, 4, 40 root 3. This would be 54. This is 200 meters per second. Yeah, easy one. It is just a differentiation there. Have a look at this. Clear? Let's see one more. We got a fixed ring. Of radius r. So someone took a rod here. This is the top view. You're looking this whole setup from the top. The rod is sliding on this ring. Meaning if I have to show you, it, this is how it will look, everyone. If this is the ring, initially the rod was here. After some time, the rod was here. After some time, the rod was here. So this is how the rod is going. The rod is moving continuously. Now we are defining the point of intersection between the rod and the ring as point P. P is a point of intersection. Just give me a minute, everyone. Yeah. Someone is knocking the door. Yeah. So P is the point of intersection of the rod and the ring. That means as the rod is moving, the P is also moving. Meaning next moment when the rod comes here, this is point P. You get it? So P is not fixed. P is moving continuously. So if you see the small picture, so this was P, this was P, and this was P, and so on. And this is your center. So if you're observing it from here, the observer is at the center, find the angular velocity of point P. The rod is going with speed V. Is the question clear, everyone? If I have to brief it up, listen again. So this was the ring. Initially, let's say the rod is here. So this is point P. After some time, the ring rod is here, and this is point P. Now, for someone who's standing on the center, if you ask him, boss, what happened to P? He will say, the P has rotated, right? Next moment, P will be somewhere here. So if you ask him, he will say, again, it rotated. So he will think P is going in a circle, isn't it? Find the angular velocity of point P. I can even ask you find speed of point P, but yeah. The radius is R. By R sine theta. I think that is wrong. I'm not sure though. Let's see. Another 30, 40 seconds. I'll show you. And don't try to take V tangential and all. It's actually gets messed up here because you don't know exactly what is the speed of P. Okay, let's see. Go back to the basics. You simply write it is rate of change of theta. So if this is point P, from here, if I take this to be theta, right, and this distance to be x, and this is your radius r. So then we know dx by dt is nothing but minus u. Why? X is decreasing. So from here we get cos theta is equal to x by r. Yeah, I think if you differentiate this, you end up with minus sine theta d theta by dt, which is equal to 1 by r dx by dt. D theta by dt is omega, and that's nothing but minus u by r, so u by r sine theta. Yeah, you guys are right. Clear with this. I should have given actually as function of theta. They're not really that tough, but yeah. If they had asked you to find the speed of point P, that would have been different. How will you find the speed of point P? The coordinates will be r cos theta, r sine theta, then you have to differentiate that. Would you get it? Or you can actually say the speed of point P ka horizontal component is u, if you can figure that out. Clear with this? That's right anyways. The next thing. So we have an equilateral triangle. Side A. We have three particles A, B, and C. We have done this in kinematics. A is chasing B with you, B is chasing with you, and C is chasing with you. They all are chasing each other. This O is your centroid. So A, B, and C chase each other. With speed u. Like this. We have done this in kinematics, atom motion, page 223. You should refer this in case you forgot. So now if you actually look at the any particle, let's say if you're looking at A from O, this is what it will look like. It looks like A is coming closer and closer and closer. This is the trajectory of A as seen by O. It will be spiraling in. So at any instant from here, this is O. If you take this vector, this angle is delta. So delta is the angle rotated by the delta or theta. Angle rotated by OA bar. So this vector O to A is continuously rotating in a circle. Find theta as function of time t. So let's get that. And the acceleration of A at time t. Two different equations. The speed is not changing, but direction is changing. So that means it is accelerating. Hope the question was clear, everyone. So that thing is not going in a line, it is spiraling in. So the vector OA bar is continuously rotating. Angular position is theta. You can say that way because theta is that angle rotated, right? See, it is like if I draw a bigger picture, you'll understand. So initially A was here, that A was spiraling like this. So if you ask O, initially it will say, okay, this is OA bar. After some time, this will be OA bar. After some time, this is the OA bar. After some time, this is the OA bar. So this angle is continuously increasing, isn't it? Theta is changing. Yeah, you will get in terms of logarithms. If you go back to that kinematics, right, it is there only. See, look at this. What we said. What you observe is a triangle which is rotating and shrinking, and they'll always maintain a symmetry such that the centroid will remain same. And then we said, look at the velocities. You can resolve the velocities into two components, u cos thetas and u sin thetas. And we said u cos thetas are responsible for them to meet. And then u sin thetas are rotating the triangle, which we ignored then because at that time we didn't need them. But what was u sin theta? U tangential, right? There. Now you know. The u sin theta by distance will give you the omega. So the u sin thetas are making you rotate. So those are responsible for rotating the triangle, and u cos theta is making you shrink. Now we combine both. Now see, let's see how will you approach from here. Take a minute. Let's see. So let's look at that story there again. This is the same story there. So u cos 30s are responsible for shrinking the triangle, and u sin 30s are rotating the triangle. That means at any time, if you try to find that distance, if you look at the distance OA at time t, so OA final was OA initial, and this u cos 30 is decreasing u, so that is minus u cos 30 into time. The distance between O and A is not constant, it is decreasing continuously. And an inequilateral triangle, the centroid will divide in the ratio of what? It will divide in the ratio of 2:1. That is 2/3 of the height. So 2/3 of √3 a by 2, which is a by √3. So this will be a by √3 minus u √3 by 2 into time. This is your vector OA at any time t. And your angular velocity will be v tangential by OA. And v tangential is u sine 30 by this guy. Multiply this will be a minus 3u 2a minus 3u t by 2 √3. Simplify this further, u √3 by 2a minus 3 ut. This is your angular velocity at time t, which is changing, which is not constant. So, but what is omega? Omega is nothing but d theta by dt. And that is u √3 by 2a minus 3 ut plus 2a. In case you forgot, integral dx by ax plus b is given by 1 by a ln ax plus b. So in this integration, we can clearly see a ka place mein we have minus 3u and b ka place mein we have 2a. So now when you integrate this, let me do that in the next page. D theta, this will be u √3 integral dt by minus 3 ut plus 2a. This will go from 0 to theta. This will go from 0 to time. So we get u theta is u by √3 minus 1 by a. That's minus 1 by 3u ln minus 3 ut plus 2a. Limits will go from 0 to t. U and u will cancel. We get minus 1 by √3. First substitute t, which is 2a minus 3 ut. Then substitute 0, we get ln 2a. Send minus inside, and ln a by ln b ka formula. This will be ln 2a by 2a minus 3u time. Yeah, this is valid as long as time is less than 2a by 3u. Because after this time, they're going to meet. So yeah, and theta goes to infinity. That's your theta as function of time t, everyone. Have a look at this step. So the main thing was here. Once you got till here, your job's done. Then it is just one integration and you'll get theta from there. This was your omega as function of time t. So your v tangential is constant. What is changing is the distance. And that distance is depending on u cos theta. So your initial distance was a by √3. And as you get closer and closer, the u cos 30 is decreasing that distance. So here it is going, actually omega is increasing. It is rotating faster and faster, not because speed is increasing, because the distance is getting closer. Are the steps clear, everyone? This would be a complete question of this. What we did in kinematics was incomplete. There we only bothered about at what time they will meet, but this would be a much better one. Question is still not over. We need to find acceleration. How do we do that? I think we did something like that. Even there also. I think we did that in CatDog, I guess. I taught you a method for acceleration, I guess. ठीक है, we'll do it again, big deal. Just think for a minute, then I'll show you. Let's listen to this thing. Now, this is a little different though. Now, when this particle is moving, right, let's consider a small time. So initially, right, it is going something like this. This is your V initial. If you give a little time, the vector will rotate a bit, V final. Now remember, the magnitude is not changing, only the direction. So in small time dt, velocity vector will rotate by a small angle d theta. So if you try to see these two vectors, they look something like this. I'm just drawing them big, V final and V initial. I'm exaggerating this, but this theta is quite small. This angle was d theta. And this was your dv bar. If you remember from triangle of vectors, dv bar is nothing but V final minus V initial. Let's take this as V initial. So there you can clearly see. So V final is V initial plus dv bar. So triangle of vectors. If you join two vectors head to tail, then the resultant vector is from the remaining tail to the remaining head. Now in this triangle, we can clearly see it's an isosceles triangle because this magnitude is V, this magnitude is V, this is d theta, and this is like a small piece here, dv. Theta is so small, I can treat it like an arc length, right? But if you don't like that, we can also take an isosceles triangle and do it. So we can say like this, since d theta is very small, we can treat dv like an arc. Then we know arc length ka formula dv is equal to radius is equal to v into d theta. So basically this y becomes the arc length. The velocity becomes the radius. So we are just making a triangle of sides v and angle d theta. If I divide dt by both the sides, we get dv by dt is equal to v d theta by dt. dv by dt is nothing but acceleration, and d theta by dt is v omega. Yeah, remember that, quite a good result. So acceleration of this body is v into omega. V is the speed and omega is the angular velocity. And omega we already know from here. This is the acceleration of the body at time t. Yeah, there's a little bit of approximations and stuff. And later on you will see this is actually radial acceleration. There is no tangential acceleration here, but yeah, quite a useful thing. You can do the same thing even for that square and hexagon things, remember, which we did? It's valid for all that stuff. All clear with this? There, if you see all these questions, right, we are just playing with that d theta by dt and everything. And the next thing, angular acceleration. Alpha. This is simply rate of change of angular velocity. So alpha is given by d omega by dt or omega d omega by d theta. Hope you can see the resemblance. They look exactly like this. Just give me a minute. Let me just remove the people whose cams are off. Yeah. So this is looking like A is equal to dv by dt, which is equal to v dv by ds. I hope you can see the resemblance there. Alpha average will be omega final minus omega initial by time. If you draw a graph of alpha versus time graph, this is the positive area. This is your negative area. Again, exactly like a T graph. So area under alpha T graph will give you change in angular velocity. If you have an omega time graph, then the slope will give you angular velocity. There you can see this thing. All this stuff is exactly the same thing as which we did. Then, if alpha is constant, then this all looks like kinematics. That's why I said it is circular kinematics. If alpha is constant, then we have our three equations. Omega final is omega initial plus alpha t. Delta theta is omega initial time plus half alpha t square. Omega final square minus omega initial square is equal to 2 alpha delta theta. Yeah, so this is the relation between them. And if you look at the relation between these angular and linear variables, in circular motion, we have done this before. So if you're going in a circle, next class, right, when we meet, then we are going to do even what if you're not going in a circle? Then things get really messed up. You'll actually get four terms. So we will see all that stuff in the next class. Derivation is not that important, but having an idea is important. So we have S is equal to R theta. If you differentiate it, so if you see here, right, R is constant, so it kind of works out. R is also variable when you have to use product rule. R d theta by dt. Then this will become V tangential. This becomes R omega. If you differentiate again, we get A tangential. We get R alpha. The vector form is this. V tangential is omega cross R bar. A tangential is alpha cross R bar. Yeah, these are your relations. And how we got the cross product, it directly comes from the direction. Everyone clear with this? Let's see one easy question on this. So this is all exactly kinematics. You just replace theta with position and velocity with omega, and acceleration is this. A fan is rotating clockwise. 240 revolutions per minute. And has angular acceleration 5/4 radian per second square anticlockwise. Find the total angle rotated in 50 seconds. Again, be careful here. I'm not asking you the angular displacement, total angle rotated, meaning you rotate clockwise or anti-clockwise, you have to add it up. So this guy is similar to distance. So it doesn't matter how the fan rotates, clockwise or anti-clockwise, it'll always add up. So be careful. Initially it is rotating clockwise, but deceleration is anti-clockwise. Let's see how will you do this thing. You fell into the trap. Now see here, it becomes a little difficult to visualize in terms of circle because this is how the fan is going. First, the fan is going like this, then it is going like this. So it looks difficult to see. So my suggestion would be convert this into a kinematics problem. It would make your life a little easy. So first, let's get the data here. What is omega? Make sure all should be in SI units. So 240 revolution per minute. So revolution is 2 pi. Radians in minute is 60 seconds. So that's 8 pi. Radian per second, clockwise. Alpha is pi by 4 radian per second square, anti-clockwise. So what I'm suggesting, consider this like a block. So the block is going with an initial speed u is equal to 8 pi, because the max relay doesn't care. And it feels like there's a deceleration a is equal to pi by 4. Now, if I ask you how is this particle traveling, what will you say? This will go front and it will take a turn, remember? So it is rotating clockwise for some time and then anti-clockwise for some time. So let's find where it is stopping. So if I take v square minus u square is equal to 2as. So this is the point where v is 0. Then this will be 0 is equal to 8 pi whole square. This will be 2 minus pi by 4 into s. So it will be 64, 128 pi. Perfect. If I use the formula s is equal to ut plus half it square, remember this will give you displacement. It doesn't give you the distance traveled. So this would be 8 pi, 50 seconds, plus half into minus pi by 4, 50 square. This would be 400 pi minus 2500 pi by 8, 32,032. This thing is 700 by 8, 350 by 4, 175 by 2, 87.5 pi. This is your displacement. That means after 50 seconds, you will be here and your displacement, whatever is 87.5. But when your velocity is zero, here your x is 128 pi. I hope you're getting it. So it's actually going till 128 and then it is coming back. So this distance here is 128 pi. This was 87.5 pi. And this was 40.5 pi. So what's the total angle rotated? So you rotated 128 pi clockwise and then 40.5 anti-clockwise, but you always add it up. How much is this? 168.5 pi. Okay, check it out. If you just convert into a distance formula, you will understand. The biggest problem here is because it is going clockwise, anti-clockwise. If I try to draw it like this, it becomes confusing. But if you convert this into a 1D motion kinematics, Max really doesn't care whether it is theta or x or u or omega or a in this thing. Everyone clear with this? So all these questions, right, are they're quite similar to kinematics. So we will not spend too much time on this. All right, let's see one more before going ahead. Alpha is equal to minus k omega. K is constant. Alpha is your angular velocity and omega is your, alpha is your angular acceleration, omega is your angular velocity. Initial angular velocity is omega naught. Initial angular position is theta naught. Find omega and theta as function of time t. We have done this before. You know where we did this? Calculus. This question, remember, A is equal to minus kV. Initial velocity u, initial position x naught, find xmt as function of time t. Exact question. I made everything into angles. So page 146. Give it a try. Exact same question, except the variables are different. Try. You got a minute or two. Clear? Hmm. Hmm. It's just a double integration there. Let's just brute force there. So we have alpha is equal to minus k omega. Alpha is d omega by dt. Yeah, bring your omega this side. Integral limits 0 to time. And initial velocity was omega naught to omega. This will be ln omega by omega naught. I'm skipping steps here. Is equal to minus kt. Then you know what to do here. Send that exponential there. You'll get omega naught into e power minus kt. Then again we integrate this d theta by dt. It was the same problem. We're just repeating the steps. Then we get d theta omega naught e power minus kt dt. Integrate again. This will go from theta naught to theta and 0 to t. This will give you theta minus theta naught is equal to omega naught e power minus kt. Ka integral is minus 1 by k e power minus kt 0 to t. This is more of a calculus problem. Minus omega naught by k e power minus kt e power 0 is not 0. Be careful with that. Theta minus theta naught. So theta will be theta naught plus omega naught by k. Send the minus sign inside. You get 1 minus e power minus kt. Check. That's your angular velocity as function of time t. Everyone clear with the steps? It's the same thing which we did in kinematics. Take a break. Come back by 9:40. We'll continue from here. So that's about circular kinematics. Next thing, we will start off with uniform circular motion. Now we will see forces and stuff. Take a break. Come back by 9:40. Any doubts so far? Yeah, hands on everyone. Let's start off. Yeah, hands on everyone. Let's things here. Uniform circular motion. We'll also simply call it as UCM. So what is this about? So the definition, right, in UCM, and later on we will see what happens if your speed is increasing, what if your radius is changing. We will see all that stuff. Otherwise, you guys need to keep your cams on. You have a problem with internet and all, you need to sort it out by next class. This is happening quite frequently. It's not like you guys don't know there is a class that is happening. Next class, I won't be allowing you, like, if you say there's internet and all, like, it can happen once or something, but for some of you, it is happening every week. And yeah, please keep your cams on. So in UCM, the particle goes in a circle with a constant speed. That's it. If you see, the definition is pretty straightforward. In uniform circular motion, the particle goes in a circle with constant speed. That's the only definition we have. Now, from here, we can actually infer a lot of things. One, now, since you're going in a circle, right, the direction is changing. So there's an acceleration. That much we are sure. So we can say the acceleration is always perpendicular to the velocity. We'll see why. Dhruv, can you just focus on the class? Right? Please focus on the class. Don't just send random messages. What is happening with you guys today, Ray? Why are you guys so distracted? Is always perpendicular to the velocity and towards the center of the circle. Now, how can we say it is towards the center of the circle and it is always perpendicular? One thing is clear, there's an acceleration. So let's look at the possibilities. Now, when you're going in a circle, your speed is u. Let's say if your acceleration is like this. Now, if you resolve the components, we'll get a cos theta backward and a sine theta this way. Suppose if the acceleration is this way, the a cos theta is opposite to velocity, the speed should decrease. Since a cos theta is opposite to u, right, speed must decrease. But It is given speed is constant. Remember, that is the only statement we have. You're going in a circle with a constant speed. The second possibility, the acceleration is this way, right? Either it is making an obtuse angle or it is making an acute angle. So this component will be a cos theta, and this component will be a sine theta. And here, if you see, the speed increases. So one thing is clear, your speed cannot change. That means you cannot have a cos theta backward or you cannot have a cos theta forward. That means there's only one possibility. A cos theta must be 0. And since speed is constant, right? So a cos theta must be equal to 0 and theta must be 90. And therefore, we proved when the particle is going in a circle with a constant speed, the acceleration is always toward the center. There. So that is the first thing. And all this thing came from one statement that you're going in a circle with a constant speed. Is that making sense? Because you can't have a cos theta. If you have a cos theta, your speed will change. We will talk about that also. The next thing. Now we can actually prove this with your regular calculus and all, which we actually did here, if you remember. So I'm not going to do that. We'll do something else. It is more intuitive. There is this guy. Look at here. Particle is going in a circle of radius r, finding the acceleration. We differentiated this vector once, we got velocity. We differentiated twice, we got an acceleration, centripetal acceleration. So this we actually proved it in calculus. But let's see something more intuitive. Now, this particle is going in a circle with a constant speed u, and the acceleration is toward the center. Take a very small time t, a very small time t, where t tending to 0. This is an important thing. Listen carefully. It will give you an intuitive thing like what is happening in the circle. This is going with speed u. Your acceleration is toward the center. Now, in small time t, what will happen? It will travel a distance of ut, and it will also fall down. So it is like a kinematics. We are assuming like a projectile motion in a very small time t. This will travel a distance of half at square. And it will also travel a distance of horizontally ut. You're getting two things are happening. Just like a projectile from a building, you're projecting with you and the acceleration is there. I know it's not exactly projectile, but the time is so small I can approximate it. Now from here, when you look at this is your radius and this distance is r minus half at square. So see what happened. In small time t, you went forward by ut and you have fell down by half at square. Now using the Pythagoras theorem, we get r square is equal to ut whole square plus r minus half at square ka whole square. When you expand this, you get r square is equal to u square t square plus r square minus ar t square plus 1 by 4 a square t power 4. R square goes off, and then you can take out t square common. You end up with u square minus ar. 1 by 4 a square t square is equal to 0. Now, since the time is very small, this term will tend to 0. And then you end up with u square is equal to AR, and we get acceleration is equal to u square by R. There, no calculus, nothing. We just used kinematics. But this thing tells you something even more. So this can be written as omega square R because we know u is equal to R omega. Let's see the interpretation of it. This is saying something. And this will be the basis for the whole thing. What this is telling you, know, if you want to go in a circle, so this thing, right? This is how you read it. If you want to go in a circle of radius r with speed u, you need to have an acceleration of u square by r. Getting it? So if you have an acceleration of u square by r, you will go in a proper circle. What if you have more or less? So listen to this. Case one, let's say if your acceleration is greater than u square by r. So just go back to this derivation again. Means what? You're traveling ut, right? But acceleration is more. That means you're falling half at square, but because your acceleration is more, think of like this, you're traveling this and your acceleration is more, so you're falling more inside. That means this particle is actually spiraling in. Is that making sense? Look at this. If you have exactly a is equal to u square by r, you know what is happening? Every time your velocity takes you forward, the acceleration will put you back on the circle. Isn't that what is happening? That is what is happening, right? Or you can think of like this. Every time your acceleration is pulling you inside, half at square, your velocity is putting you back on the circle. And this is happening at such a minute level, it feels like, it's just going in a circle. But now if your acceleration is more than required, then what do you think will happen? You will fall more, but you will go less here. That means you will not fall on a circle anymore. Then your motion will look something like this. So you will fall more here and you will reach here. So you will spiral in. So if you give acceleration more than u square by r, the particle will spiral in. Case 2, if you give acceleration less than u square by r, means you will fall less, but you will go outside more. You will spiral out. So if you want to go in a circle, you need to give that exact u square by r. No, don't say like that. Think of like this, Ahana. If you are going in a circle of radius r with you, if you want to satisfy these two, you need to give this acceleration. Or if you say I give you this acceleration, you have to go with u and r. And again, see, we proved this. We didn't randomly, this thing didn't come out of thin air. First, we proved, and see, we all proved all this stuff with just one statement. The particle goes in a circle with constant speed. That's it. So first we proved there is an acceleration, and then we said it is towards the center. Then we said for small time t, right, the acceleration will try to take you toward the center. That is half at square, but your ut will put you back on a circle. And this happens precisely for only one value of u square by r. This does not happen for any other value. Is this making sense? Let me ask you a question on this. Is sun attracting the earth? Sun is attracting the earth, right? Then why is earth not falling into the sun? What do you guys think? See, if someone catches you and pulls you, won't you go towards them? If sun is attracting the earth, why is the earth not falling into the sun? Assume earth is going in a proper circle. What do you guys think? This one thing will explain what is uniform circular motion. Speed is, and who is balancing the attraction then? If sun is attracting the earth and earth is not falling into the sun, is someone balancing the earth? Who? Pseudo force doesn't exist. Centrifugal force is not real. You guys have studied this in school. Centrifugal force is just a mathematical correction. Pseudo force, you have created it for the solving problems. It doesn't exist. So the answer for that question, right? Motion is cancelling force from when? The sun attracts the earth. If sun attracts the earth, why doesn't it fall into the? The answer for this question, right, is this. There is no one balancing the earth. The earth is always falling into the sun. The answer is the earth is always falling into the sun. But then what is happening is this. Every time the earth falls into the sun is pulling. Your velocity ut is putting you back on a circle. Again, I'm exaggerating it, but happens minutely. Again, the earth falls into the sun. Then your velocity ut is again putting you back on a circle. So the earth is always falling into the sun. If you just make the earth ka velocity zero for a moment and leave it, it will go straight into the sun. So there is no one who is balancing the earth. Earth is not in equilibrium. If by chance suddenly sun starts attracting earth more strongly, then what will happen? You get more acceleration, then it will become this case, isn't it? For some reason, let's say sun is attracting the earth double strength. Then suddenly acceleration will become more than u square by r. Earth will spiral into the sun. If earth attracts the sun attracts the earth lesser, then it will spiral out. So earth is always falling into the sun. There's no one balancing it. The velocity puts it back on the orbit. There. So we proved few good things here. Which part, Ahana? That is a self-explanatory statement there. I'm not sure which part you want me to explain again. Sun is attracting. So technically, Earth should go toward the sun. Every time it goes toward the sun, the velocity is pushing you horizontally. So you get back on the circle. Again, sun is attracting. You fall. Again, it pushes you back on the circle. So this is happening at every instant. So it gives you a feeling as if it's not falling, but it is actually falling every instant. So there is no one who is balancing it. Clear? Now, there with that all that stuff. So let me write down the final statement here. So this is how you should read it. If a particle wants to move in a circle, if a particle wants to move in a circle, of radius r with speed u, there has to be an acceleration. It needs to have an acceleration. So this is the misconception people have. People think because you're going in a circle, there is an acceleration, which is wrong. You have acceleration, that's why you're going in a circle. It needs to have an acceleration. It is the other way around. You don't generate acceleration because you're going in a circle. It needs to have an acceleration u square by r. And this acceleration won't come just like that. It has to be provided by someone. This has to be provided by an external force, right? So acceleration, you won't get it like just like that free of cost. This force, right, is called centripetal force. Whoever provides the force to make you go in a circle is called centripetal force. So centripetal force is not some new force. Right? And the acceleration is called centripetal acceleration because it's toward the center. So remember this thing. You want to go in a circle, you need to have acceleration. And that one, someone has to give you. It is not the other way around. People think you're going in a circle, the acceleration aa jayega. No, that doesn't work that way. It's not like that. The acceleration is called centripetal acceleration. And centripetal force is not some new weird force or something. It's your standard forces, like whoever is providing. Example, if you take sun and let's say Earth is going in a circle. So here the gravitational force is providing that acceleration for you to go in a circle. So the gravitational force is a centripetal force. So don't think gravitation is separate and centripetal force is separate. Gravitational force is centripetal. Suppose if you take a block here with a string and if it is going in a circle. The tension in the string is a centripetal force. The moment you cut the string, tension becomes zero. The tension becomes zero, A becomes zero. Because A became zero, it becomes this case. A is less than u square by r, you will spiral out. I hope you're getting it. It is always that way, other way around. You don't get acceleration because you're going in a circle. That's it. That is the whole point I want to say. Just remember that. You won't get acceleration because you're going in a circle. You have acceleration. That's why you started going in a circle. If you take a proton and an electron, the electrostatic force is a centripetal force. So the spring force, friction, all these things are right. These are only the centripetal forces. So centripetal is not some new force. What is centrifugal? For now, just forget about it. There's nothing called centrifugal. It doesn't exist. We will talk about that in more detail in the next class. It is actually a pseudo force, but the story is more than that. But for now, let's see this thing. So how do we solve questions on this? Again, go back to the basics. Step 1, choose a system, draw the free body diagram. Step 2, assign accelerations and find the relation using constraints. Now here, step 2 we change something. If you see in friction, right, we changed step 1 by adding friction. In circular motion, we are going to change step 2. We are going to add the acceleration term. So let me give a simple question. Let's say we have a block of mass m going in a circle with speed u. This was radius r. This was going u. So step 1, free body diagram. What are the forces? Tension, your own weight mg, normal reaction. And you're going in a circle. So this is the statement we'll make. Since you are going in a circle, there must be a centripetal acceleration, which is given by u square by r. Why? If this acceleration is not there, you won't go in a circle. Are you clear with the statement? So we proved this. And then you're done. FBD is done. So since it is going in a circle, it must have acceleration. So that is step 2, assign your accelerations. Step 3, resolve forces, write F is equal to ma. Step 4, solve. So the only new thing that you learned is that extra acceleration. It must have centripetal acceleration. And then we apply F is equal to ma. Then we will say tension is equal to mass into centripetal acceleration, which is mu square by r. And that's your answer. Is that clear, everyone? Simple. So I hope how we derived it. If you see, I didn't use any calculus, nothing. I kept it everything intuitive. The whole thing we just started with one statement. You are going in a circle with speed u. That's it. From there we derived everything. We said A is perpendicular, then we got the value of A. And so understand the meaning of A is u square by r. It's not the acceleration which is generated because you're going in a circle. You're going in a circle because you gave that value. So let's see a question on this. Top view. Let's say we got a rod. The left-hand side is fixed. We have 3 particles. Let's say M, 2m and 3m. So we have three pieces, like three particles attached to the rod. Uh, Ever been to Barbecue Nation? You can think of, like, that grill with the three paneer pieces. Can you imagine? There. Now you imagine it. So this whole setup is rotating with omega. This is lentil, this is lentil, and this is lentil. So they're all equidistant from each other. So the tension in the rod is T1 and T2 and T3. The rod is massless. It's a light rod which is rotating in a horizontal plane. Find T1, T2, T3. Three masses, M2, M, 3M, are attached to a light rod rotating with omega. Find T1, T2, T3. You can type your answers, right? This is not that difficult to type. Nerana. Is that 3 or something else? Again, remember, this is simply NLM. There's nothing different. Don't think it is circular motion. Remember, I kept telling you NLM is like plain dosa, friction is like masala dosa. This is something you're just adding one more ingredient. The only new thing you learned is if something is going in a circle, it will have an acceleration u square by r. Other than that, everything else you already know. Let's see. Step one, draw the free body diagram. So this is fixed. This is 3m. This is m. This is 2m. So everyone here is going in their respective circles. And let's start from 3m. Draw the free body diagram of 3m. What are the forces? We will write only the horizontal forces. Let the tension be T3. That's it. There is no other force. Then we will say, since you are going in a circle, there should be an acceleration, which is omega square into radius, which is 3L. Remember, don't use u square by r here because omega is same for everyone. Speed is different for different. Everyone is going with different speeds. This is going with L omega. This is going 2L omega. This is going 3L omega. The farther the particle, the faster it goes. So omega is the preferable choice. Omega square into 3L, that's your radius. So what is the tension? T3 will be 3 times mass into acceleration. That would be 9m omega square L. Next thing, draw the FBD of 2m. What are the forces on 2m? Now remember, there are rod on either side. So this is pulling with T3, rods are pulling here, and this is T2. And then we will say, since you are going in a circle, you will have an acceleration which is AC is equal to omega square into radius, and your radius is 2L. So T2 minus T3 is 2m into omega square 2L. But T3 is already 9, so T2 will be 13 m omega square L. Hope you're getting it. So you're just putting the free body diagrams there and putting the forces. Now we'll draw the FBD of M. And this is your T1 and this is your T2. Again, the same argument. Since you're going in a circle, you should have an acceleration. And that's not random. We proved it, right? So, and then we will say, so who is the centripetal force then here? So T1 minus T2 is the centripetal force. So both the tensions together are generating that acceleration, which is m into omega square L. T1 is 14 m omega square L. Please have a look at that. All clear with the steps? Make sense? Let's see one more. So there. So if you think about that, right, in terms of that NLM, the only thing you're adding is the acceleration. So let's say we have a length L, we have a mass M. This guy is going in a horizontal circle. This is called as conical pendulum. So remember the terminology. You're getting how it is going? It is going in a horizontal circle. So particle of mass M is going in a horizontal circle. Find the tension, speed, and the time taken for one revolution. Same thing. Step one, start with the free body diagram. Let's see. Step one, choose your system. The particle is my system. Forces, tension, mg. That's it. There are only two forces. Again, I'm saying forget about centrifugal force and everything. I still didn't teach you it, so we will talk about it. So let's be clear about a few things here. And this angle is theta. That's it. There is no other forces. Then you'll come and argue. Since you're going in a circle, there should be an acceleration towards the center. That's it. There is no argument there. Like, and we have proved this. And whenever you think like why, you again go back to the story and you will show that derive the whole thing again. So then you will say it should have an acceleration toward the center, which is u square by r. And now when you balance the forces, you can clearly see this. The radius will be this was L, this was theta. The radius was L sine theta. So T cos theta is balancing your weight. So from here, you'll get the tension directly. And who is providing the centripetal acceleration? T sine theta. This will give your mg tan theta will be mu square by r. This will give you a speed. Time taken will be 2 pi r, the circumference by speed u. Substitute here, and this would be 2 pi r by root r g tan theta. This would become root pi L cos theta by g. You have to substitute r is sine theta here and you'll get it. All clear with this? Again, did I do anything new? The only thing we are adding is centripetal acceleration. See, that's what I keep telling you. Don't think you're learning something new. Always ask yourself, okay, in this, how much is repetitive and how much is actually new? You keep doing that and then you'll not find things are getting overwhelmed. You'll feel like, okay, it's just a connection. All clear with this? Let's see one more. These are easy stuff. We got a big cylinder here. Which is rotating with omega. Now, in Europe, right, there is a ride like this. It's called death rotor. No one dies, but the name is there. So in this, what we do, we take people and we keep them on the edge. And this is a rough cylinder. At the bottom part, right, they put you inside and they start rotating and they open the bottom part. So if you can rotate fast enough, you don't fall down. For some reason, you just stick to the walls of the cylinder. A person stands with his back touching the walls of the cylinder. Right, touching a walls of a rough rotating cylinder. So find omega so that he does not slide down. If you don't rotate fast enough, you're going to slide. This, right? Look at this. So they have kids there. They kept them in a cylinder. Now they started rotating the cylinder there. It's rotating with omega. Look at the kid here on the right with his glasses. Yeah, he's getting scared, but yes, it's rotating fast enough. Now look at the floor at the bottom, huh? There, the floor goes off. Did you see? And they don't fall down. Look at this thing. It looks like he's falling down. Yeah, it is sliding a bit. But you remember that statement you learned in friction? Frictional force is independent of surface area. So even though his contact is decreasing, he still has enough friction. Now he is slowing down. Okay, now as they're slowing down, now friction decreases. You can see how they're sliding down. And then down. Yes, that's our question. So it does actually happen. It's not just our imagination. So let's get this omega. Let's save the person. So that's a right. You must have seen in circus also, right? People take this car and the bike and they go round in that dome kind of thing. The idea is same. That's called a death well. If you have heard that recent song, right? I think not recent, I think year-old one, that Hanuman kind of song. It became quite famous. And that he does that. That takes a car and goes round and everything. Again, same story. Step one, choose your system, draw the free body diagram, assign acceleration, apply physical demo. So, like if you see like a broken tape recorder, I keep saying the same thing. Because in the exam, when you're tensed or when you're not getting an idea how to start a problem, at least if you have a process, right? The important thing is that you need some momentum. Once you start with few steps, your brain will start figuring it out. Just staring, just stand there staring and blanking out. That's a problem. So what are the forces? Normal reaction. There is a friction which is pulling you up, and there is an mg. That's it. There are only three forces. There's no other force. And then we will argue because you are going in a circle, you should have an acceleration, which is omega square r. And we can clearly see here normal reaction is the centripetal force. So here n is providing the required centripetal force, m into acceleration. So n is m omega square r. And friction ka value is equal to mg. Be careful, don't write maximum. We don't know, he's not slipping. And this friction must be less than equal to fs max. I need only mg to stop you from slipping. I'm not sure whether this is greater than or less than maximum. So this is equal to mu n. This is less than equal to mu m omega square r. And this would give you omega is greater than equal to root over g by mu r. There, if you see, right, all these problems we are doing with centripetal acceleration. But as we keep going ahead, you will notice this thing it really is not that intuitive. Meaning, at some point, right, it starts becoming a little weird to have two problems with this. So centrifugal force really helps you there. It gives you an feeling. For example, the same question, if I say you are going in a circle, because of that you got a centrifugal force which is pushing you away from the center. That force is providing normal reaction, and because of that you're getting friction. It becomes more easy for you to visualize. You're getting it's completely wrong. N is giving acceleration. It is not like centrifugal force is giving you N. But for the sake of problem solving, it makes your life easy. So we introduce something called pseudo force, centrifugal force and all that stuff. But in reality, centrifugal force is a type of a pseudo force, and there are four pseudo forces. That's a big working there, which we'll do in the next class. But today we will do some basic things which are required for that derivation. So let me show you those stuff. We will get the ingredients ready today. We have done this before, but let me show it again. So let's say if I take a circle, let's say this is r cap, a unit vector, polar coordinates, if you remember, which I did teach you before. So this is your r cap and this is your theta cap. So r cap is your unit radial vector. Theta cap is your unit tangential vector. So we're taking clockwise is anti-clockwise is positive, clockwise is negative. Away from the center is positive, toward the center is positive. All these are this thing, what do you call it? Polar coordinates. I think we did this thing in basic math and vectors. There are cap, theta cap, so that is a thing. Anyway, I'll just show you better. I deleted something. Now, if you just drop a perpendicular from here, we get r cap is, it's a unit vector, so 1 cos theta I cap and 1 sin theta j cap. And similarly, if you take theta cap, this is theta, this is 90 minus theta. So theta cap, you can clearly see that would be minus cos 90 minus theta. That is minus sin theta I cap plus cos theta j cap. So this is how you write your r cap and theta cap in terms of this. So this is your tangential vector and that's your radial vector. Now, if I differentiate this, dr cap by dt, this becomes cos theta, becomes minus sin theta I cap. And this becomes cos theta d theta by dt j cap. D theta by dt is nothing but omega. And if you observe here, this is minus sin theta I cap plus cos theta j cap, which is your theta cap. If you remember, we proved this. Every time you differentiate a vector, right, you are going to get a vector which is rotating 90 degrees anti-clockwise. So when you differentiate a radial vector, we get a omega theta cap. A better way of writing is omega cross r cap. Because see, omega is upward, it's a pseudo vector. This is r cap. This is omega cap. So omega cross r cap will give you a vector this way, theta cap. Cross product everyone. Similarly, if I differentiate this guy, d theta by dt, this would give you minus cos theta, d theta by dt I cap. Again, the end result is more important, so derivation ke liye we will need this stuff, minus sin theta, d theta by dt j cap. And if you observe this, that becomes minus omega cos theta I cap sin theta j cap, which is minus omega r cap. This can be written interestingly in the direction of omega cross theta cap. If you do omega cross theta cap, you get minus r cap. And notice something. Did you notice something? When I differentiate r cap, I got omega cross r cap. When I differentiate theta cap, I got omega cross theta cap. From here, we can make an argument. Whenever you differentiate a unit vector, you get omega cross that particular unit vector. So now we can write it in more general form. So if you have a vector a bar, can be written as mod a into a cap, magnitude into unit vector. So when I differentiate dA bar by dt, I can differentiate this thing as dA by dt a cap plus a into differentiate dA cap by dt. just now we proved here, the general form dA cap by dt is omega cross a cap. So where omega is the angular velocity of rotation of that a bar vector. So if that vector a bar is rotating, then it makes sense. If it is not rotating, then it is zero. The direction is not changing. We get this. So this can be written as dA by dt a cap plus a into omega cross a cap. I can send that a bar a inside, then this will become dA by dt a cap plus omega cross a bar. So there, this is a much better one. So if you differentiate a rotating vector, you get dA by dt a cap plus omega cross a bar. If it is not rotating, this term becomes zero. That means your direction is constant. There, this is a proper vector form. So when you differentiate a vector which is rotating, so you're differentiating the magnitude and the direction separately. Is this clear, everyone? Right, so remember this thing. We will need this. So next class when we catch up, we'll continue from here. Make sure to just go through this again. Like I said, the final result is more important because what I'm going to teach you now is technically out of portion. So whenever they ask you this, they will give it in a paragraph, which they did 2018, 16. Coriolis force and all that stuff, there's not in the portion. So they will give you a paragraph, they'll explain you a bit, and then they'll ask questions on it. But and they have a tendency to do that. So we will do that anyways. And we will see little more different models also. But that I think the main idea you got. What is centripetal accretion? We'll talk about pseudo forces in the next class. With that, we'll wrap up for the day. We'll continue again on Wednesday, same time. So any doubts, anything else, please stay back and ask, or else you're free to leave. And there is a test online, so make sure to give. Friday 11:30 is the deadline.